Now let's talk about nonlinear SVM. So we have seen linear SVM and the soft margin SVM, but these are linear classifiers. And because almost every real-world problems are nonlinear, so it is almost impossible to apply these linear classifiers, linear SVM, to these real-world problems. So that's why we need a non-linear SVM. So what is non-linear SVM? The basic idea of non-linear SVM is the following. Suppose we have a data X, and also suppose this data is not linearly separable. So this problem is non-linear. Then in non-linear SVM, we actually expand the original dimension of data into higher dimension. So for example, the original input dimension is like 10. Then we expand this dimension into a higher dimension like 100, 1000, or sometimes infinity. So expand this to very, very high dimension. Then in higher dimension, the data becomes very sparse. So because the data is very sparse, it is very, very much likely that these data are linearly separable in higher dimension. So in higher dimension, because it is most likely that the data is linearly separable, we find a linear line with maximum margin in higher dimension, okay, just like we did in linear SVM. So we find line with maximum margin in higher dimension, okay, and then after that, after we find this linear line with maximum margin in higher dimension, we transform this expanded dimension back into original input dimension. Then the line in higher dimension now becomes non-linear curve in original data dimension. Okay, so that's the basic idea of a non-linear SVM. So the linear classifier in the expanded dimension, feature space means expanded dimension, higher dimension. So linear classifier in the higher dimension is equivalent to non-linear classifier in the original dimension. Input space means original data dimension. So for example, in the XOR problem, XOR is well-known non-linear problem. So, but if you add one more dimension like x1, x2, now it becomes three dimension. Then in this three dimension, expanded dimension, data is now linearly separable. So this is the example of the expanded dimension where data is now linearly separable. Okay, this slide kind of repeats what I said in previous slide. Okay, so how in SVM how to handle nonlinear cases in SVM. Okay, so to deal with nonlinear separation, okay, actually we transform the input is here. Okay, we transform input data into another space, usually of much higher dimension. Okay, so input data, the dimension of input data is expanded into a very higher dimension. Okay, that's basic idea. And then in higher dimension, we find the linear line, linear decision boundary, linear line. Okay, and so we find the linear line in a high dimension. Okay, and that is mapped back to the original dimension. Okay, that's basic idea. We have some terminology here. Okay. Feature space is the data space of expanded dimension. Okay, I said we expand the input dimension into higher dimension, right? So that expanded dimension is called a feature space, and the original data space is called input space. Okay, so you're going to see these terminology many times later on. Okay.
Okay, this picture shows the example of the dimension expansion. Okay, how we expand the dimension. Okay, from input space to feature space. So as I said, input space is the original dimension space, and the feature space is the data space of expanded dimension, right? So in this picture, in the left hand side here, this is original data. Okay, it's two-dimensional data, and we have two class values, red and blue, right? And yeah, definitely this is non-linear problem. Okay, we cannot solve this problem using line. Okay, no way we can do it. So this is definitely non-linear problem. Okay, so how do we solve this using linear classifier SVM? Okay, then I said we expand dimension. So let's expand this two dimension into three dimension case like this right here. Okay, so it is the same data is dimensionally expanded to three dimension like this. Okay, so as you can see here in three dimension space, in feature space, we are able to find this linear hyperplane. Okay, this is not line, this is sorry, hyperplane. Okay, because this is not line anymore. Okay, a linear hyperplane. Okay, so in higher dimension we are able to find a linear hyperplane. Okay, and then if we transform this linear hyperplane back to the original input space, then it will look like this circle. Okay, so that's basic idea. So in nonlinear SVM, we have original dimension, input dimension, right? And we expand it into higher dimension. In this case, it is expanded to three dimension. Okay, so in expanded dimension, higher dimension, we find a linear hyperplane. Okay, it's not line anymore in higher dimension. It's hyperplane, linear hyperplane. Okay, and then this linear hyperplane is mapped back into the original input dimension. Okay, so which linear hyperplane now becomes circle in original dimension. Okay, that's basic idea of nonlinear SVM. Okay, this is another example of expanding dimension. Okay, this is a one dimension case. The input space is one dimension data. Okay, so here, this is okay. Okay, this is in input dimension. This is linearly separable problem, so we don't have to worry about non-linear SVM, whatever. You can simply use linear SVM or whatever. It's a very simple problem, so you don't have to worry about this data. Okay. But in this case, even though it is one-dimensional data, it is non-linear problem. Okay, we cannot solve this problem using line, right? It's clear, right? So how to solve this non-linear problem using SVM? Okay, then again, as I said, we expand the dimension. So in this case, the original input space, input dimension is one dimension, right? So we expand this to two dimension. So this original input dimension, this original input is expanded into two dimension. Okay, so this is the picture of two dimension, expanded dimension, right? And how do we expand the dimension? This is the configuration. So this is original data X. Then when you expand into two dimension, this is the mapping. Okay, we have two dimension. The first one is X, second dimension is X square. Okay, so that's how we have all this data in these two dimension. Okay, so this is mapping pi X. This is mapping from this one dimension data to this two dimension data. Okay, this is the mapping. Okay, so again, in summary, in nonlinear data set, we cannot use linear SVM, right? So to solve it, we expand the input dimension into higher dimension. Okay, in this case, one dimension is expanded to the two dimension. Okay, So in higher dimension, we find linear classifier. So in this case, in 2-dimension case, we are able to find this linear line here, right? So in higher dimension, we find linear line or linear hyperplane, okay? And that line is mapped back to the original dimension, okay? So that's how it works in nonlinear SVM. So I said nonlinear SVM actually expands the input dimension into a higher dimension, right? So that means we have a mapping from input space X to feature space F, okay? So here, let's say X is the input space, input dimension, okay? F is the expanded dimension, feature space, okay? Then we have a mapping from input space to feature space, right? So X data, original data, X is transformed to another data using this mapping pi, right? So we have mapping. So you expand dimension means we have mapping from input dimension to higher dimension, okay? Let's say that mapping is pi, okay? So for example, here, let's say the original data is x1, y1, x2, y2, etc. Okay, then let's say we have a mapping. Mapping means we transform input data to higher dimension, right? Then this x1 should be mapped to this, and x2 should be mapped to this, etc. Okay, so every data is mapped to a higher dimension through this pi mapping function, okay? So for example, here in this is input space, we have data, and this is nonlinear, right? So it is a feature space, that means higher dimension, right? So every data is mapped to a higher dimension using this mapping, pi mapping, okay? So in higher dimension, we most likely you're gonna find a linear line here, okay? So there is mapping from input space to feature space. Okay, here is the example of mapping from 2-dimension data to 3-dimension data. So this is the original 2-dimension data, x1, x2, and we have mapping here, and this is mapped to this 3-dimension data, okay? For example, we have 2, 3 in original data dimension. Then this is mapped to this 3-dimensional data. So now it becomes 4, 9, 8.5. Okay. So we have seen that in nonlinear SVM, we expand the dimension into higher dimension and find linear classifier in higher dimension, right? And the question is, can we, is there any guarantee that we find linear classifier in higher dimension? Okay, that is the question. Okay. Actually, the answer is no. Okay. So there is no guarantee that we find linear classifier in higher dimension. Okay. So expanding dimension doesn't necessarily mean you find the linear classifier in higher dimension. Okay, so we have a problem. So actually we have a couple of problems in expanding the dimensions to higher dimension. The first dimension is, as I said, so you wanna expand the dimension to a higher dimension. Then more specifically, to which dimension you want to expand it to, okay? So which dimension you want to expand it to? Suppose your input dimension is 5. You want to extend this to 10 dimension or 20 dimension or 100 dimension, etc. Okay? In some dimensions, there is linear classifier, it's fine. But in some other dimensions, there is no linear classifier there, okay? And the thing is, we have no clue which dimension works. Okay, that's the first problem of expanding dimension. Second problem is, so suppose we picked a particular dimension, okay, for whatever reason. We selected one particular dimension, okay, and then in that particular dimension, what is the configuration of the variable in the dimension, okay? So in that dimension, we have a lot of combinations of variable there. So what is the configuration? We have almost infinite number of configurations in the dimension, right? And again, in some configuration, we have linear classifier there, but in some other configuration, we do not. Okay, so this is another problem. Okay, so we have no idea what which dimension we should extend it to, and second problem is what configuration do we have to choose. Okay, so we have no idea. Okay. Okay, in previous slide, we have seen the problems of extending dimension to higher dimension. Okay, so basically, there are a lot of dimensions and configurations, and we have no idea which dimension and configuration we should go with. Right, that is the problem. You may think, how about exploring all the possible cases of dimension and configurations. Okay, then that is nonsense. Okay, the number of dimension, number of configurations is infinite. Okay, so that doesn't make sense. It is definitely not something on the table. Okay, so in this slide, it explains another problem of expanding dimension. Okay, it is called the curse of dimensionality. So if you increase the number of attribute, increase the dimension, increase number of attribute, okay, then the thing is, the number of data you need to train the algorithm grows exponentially. Okay, so if you simply add one or two attribute, then the number of data required to train the algorithm grows exponentially. Okay, so that is the problem. So what in real world, what happens is, and you have a algorithm and you have data, and the data you have is far less than the number of data required to train the algorithm. Okay, so in most cases, the algorithm suffers from overfitting. Okay, let me repeat. If you simply add the attribute that increase the dimension, okay, then the number of data you need grows exponentially. Okay, so in practice, what happened is the data we have is much smaller than you need to train the algorithm. Okay, so data simply lacks the data. Okay, it doesn't have enough data. Okay, so because of the lack of data, it suffers from overfitting. Okay, and that is called the curse of dimensionality. Okay, so if we increase the dimension, your algorithm is cursed. Okay, cursed in this case means it suffers from overfitting. Okay, let me give you an example. Okay, let's say we have one attribute, and the attribute has 10 values, 10 different values. Okay, for simplicity, let's think about the complete data. Okay, and then in one attribute with 10 attribute values, we need 10 data, right? I'm talking about the complete data. Okay, then if we have two attribute, okay, two dimension, then the number of data now becomes 10 times 10 is 100, right? So to keep going, so if we have 10 attribute, then the number of data is 10 to the 10th, which is 10 billion, I think, right? So if you have 10 attribute, now the number of data is 10 billion, okay? When we have one attribute, the number of data is 10, I'm sorry. And the number of attribute is 10, okay? Then the number of data you need is 10 billion, okay? So you compare the growth rate between attribute and number of data, okay? So maybe, if you have the number of attribute is like, I don't know, maybe 100, then the number of data you need is 10 to the power of 100, okay? I think definitely that number is bigger than the number of molecules in the entire universe, okay? So, that's the curse of dimensionality, okay? So if you expand the dimension, this is the third problem. Okay, we have curse of dimensionality, so we need lots of data to train it. Okay, so that's the third problem. Okay, so in summary, expanding input dimension to higher dimension, this idea is very good. Okay, this idea is very novel. Okay, it makes sense, but in practice, it causes a bunch of problems, okay? Which dimension or which configuration and the curse of dimensionality, okay? All these problems. So we have to solve all these problems, okay? So basically, SVM, nonlinear SVM is kind of stuck here, okay? It's stuck. We have nowhere to go, okay? It's stuck there, okay? So when you are stuck, okay, you have to think outside the box, right? So when the algorithm SVM is stuck here, okay, we have a breakthrough, okay, and we have breakthrough, and all these problems, okay, the number, which dimension, which configuration, or this curse of dimensionality thing, all this problem is solved by a very simple method called Kernel method, okay. And this method, kernel trick, sometimes called kernel trick, this kernel trick solves all these problems I mentioned, okay? And this is the beauty of SVM. Because of this kernel technique, we solve all these problems, and also this kernel technique solves nonlinear problems, okay? So personally, I think this is the beauty of SVM, and this is sometimes the technology is beauty, and I think this is one of the examples, okay? Okay, now let's talk about the kernel method, okay? And before we go into a kernel method, let's take a look at this dual problem of SVM first. Okay, so this is the dual problem of SVM. Okay, actually this is the softmax case. Okay, it doesn't matter whether it is linear SVM or softmax SVM. It doesn't matter. Okay, so this is the dual problem of SVM. Okay, so do you remember that earlier I said that we changed primary problem of SVM to dual problem, okay? And there are some reasons for that, okay? Why do we change primary problem to dual problem, okay? There are a couple of reasons, okay? Yeah, for example, this dual problem here, this dual problem is much easier to solve than a primary problem. And the constraint here in dual problem is equality. Okay, it's much easier to handle, but in primary problem, the constraint here is inequality, right? So it's more difficult to handle, right? So there are many advantages, okay, but the most important reason, okay, the most important reason of changing primal to dual is because we can use kernel in dual problem, okay? In primal problem, we cannot use kernel method, but by changing primal to dual problem, we are able to apply kernel method in dual problem, okay? That is the most important reason why we change primal problem to dual problem, okay? So let's take a look, okay? So this is dual problem, okay? And so I said in nonlinear case, so this is linear case. So in nonlinear case, the idea was what? The idea was we map the original data, okay, the original data of original data, you map the original data to higher dimension, right? And then in higher dimension, we find the linear classifier there, right? That's the basic idea of nonlinear SVM, okay? So suppose we expanded input dimension to higher dimension. Suppose we expanded, okay? You decide the number of dimension and you decide the configuration, okay? Basically, you can say you decide the mapping, okay? You decide mapping means mapping determines number of dimension, number of dimension, and the configurations, right? So suppose we expanded input dimension to higher dimension, okay, and that means we have mapping, okay. Then in extended space in higher dimension, the SVM problem looks like this, okay. Does it make sense? Now the data is in extended dimension, okay, feature space. The data is in feature space. That means data is in extended higher dimension, okay. So the rest is the same, okay. The only difference here is original data X is now mapped to a higher dimension, okay. This is mapping. So original data Xi is mapped to a higher dimension, right? And also this Xj data is also mapped to a higher dimension, okay. The rest is same, and this part is the only difference, okay. So this dual problem is the dual problem in original input dimension, okay. But in nonlinear SVM, I said we expand the dimension, okay, and we solve SVM. We solve SVM problem. Basically, we find linear classifier in extended dimension, right? So this dual problem is the SVM problem in higher dimension, feature space, right? Do you know what I mean? Okay, I hope you do, okay? So if we solve this problem, okay, the SVM problem in feature space, then we are done, okay? Solving this problem means we find linear classifier in higher dimension, right? Because every data is mapped to a higher dimension here, right? So solving this problem means we find the linear classifier in higher dimension, right? Okay, good. Then if you look carefully, the only thing we don't know is this pi xi, pi xj, okay? The thing is, so you're gonna solve this problem, okay? All the other things are, this minor is no problem, okay? But for this, actually we do not know this mapping, and we do not know this mapping, okay? Do you remember, when you expand the dimension, okay, we have no idea which dimension we're gonna expand it to, and then we have no idea what configuration you're gonna go with, right? So we have no idea, okay? That means we have no idea of the mapping, okay? You don't know which dimension, we don't know which configuration. That means we have no idea of this mapping, okay? We have no clue about this mapping, okay? That means we cannot calculate this mapping value, right? So that's the problem, okay? If we solve this problem in higher dimension, we get the linear classifier in higher dimension, okay, then we solve the problem. But problem is, we do not know this mapping, okay? We do not know this. We do not know this pi xi, pi xj. We have no idea, okay? Because we do not know the mapping, because we do not know the dimension, we do not know the configuration, we have no idea, okay? I told you in previous slide, okay? So that's the problem, okay? So we are stuck, okay? That's why we are stuck, the SPM stuck here. And then we have a hero, okay, called the kernel, and the kernel comes in and solve all this problem, okay? All these problems are solved by kernel method, okay? Okay, as we have seen in previous slide, this one is the dual problem of SPM in extended dimension, okay? Because this data here, the original data X is mapped to a higher dimension, okay? So this is the SPM problem, SPM dual problem in extended dimension feature space, okay? And the problem was, okay, so we cannot solve this problem because this mapping, we do not know the value of this mapping, okay? Because we do not know the dimension, number of dimension, and also we do not know the configuration, etc. Okay, so because of that, we do not know this mapping. Okay, so that is problem, and that's where this SPM stuck. Okay, but if you look carefully, what we need is the mapping of xi times mapping of xj, okay? Actually, we do not need the individual value of pi xi and pi xj. We do not need these values separately, okay? What we need is the product, the multiplication in a product between these two data, okay? So even though we do not know each value of mapping here, as long as we know the multiplication value here, then we are okay, right? That's the key, okay? That's the key of kernel method, okay? So at the bottom here, we do not need to calculate each value of mapping xi and mapping xj. We do not need to know this value, individual values, okay? What we need is the inner product between these two, okay? Then we are fine, okay? Okay, in previous slide, we need to compute the inner product of mapping, okay, in dual problem. And that was impossible because we have no idea what this mappings are, right? Because we don't know the dimension, we don't know the configuration, etc. Okay, so it is impossible to compute the inner product in the dual. Okay, but in the kernel method, actually, this is the kernel method. Okay, actually this inner product, you don't have to compute inner product, okay? In kernel method, it says inner product can be replaced by a function, okay? So this is kernel method. So this inner product of mapping here, you don't have to compute these values, okay? These values, this term here, is replaced by a function, k. Okay, that is kernel method. Okay, so you don't need to worry about mapping. Okay, that means you don't have to worry about the dimension, configuration, etc. Okay, you don't have to worry about this whole thing, and you simply replace this by a function. Okay, and this function is called kernel function. Okay, so that's the kernel method, kernel trick. Okay, and that makes our life much easier. We don't have to worry about this mapping. Okay, that means we don't have to worry about the number of dimensions, the configurations. Okay, simply you replace this by a function, and that's it. Okay, so this is the breakthrough in nonlinear SVM. Okay, so what is nice about the kernel function is, let's say you picked a kernel function like this. Okay, this one. By the way, this is called a polynomial kernel. So this kernel replaces this inner product of mapping, right? So you choose this kernel function. And one nice thing about this kernel function is this kernel function actually automatically determines the number of dimension and also determines the configuration of the dimension. Okay, so if you choose, for example, here a polynomial kernel like this, then it actually maps the original data into this higher dimension. Okay, in this case, this 6th dimension, and the configuration of this higher dimension looks like this. Okay, so it automatically determines the number of dimensions and also determines the configuration in the higher dimension. Everything is automatic. Okay, that's the beauty of kernel function. Okay, you don't have to worry about this. Okay. When you run SVM, it's pretty much the only parameter you can consider is the kernel function. So then what exactly is kernel function? Okay, can we somehow pick one arbitrary function and use it as a kernel function? Okay, so actually when you run SVM, actually there are already well-defined kernel functions you can choose from. Okay, so you can just pick one of them and use it as kernel function. That's easy. Okay, and or if you want to come up with a new kernel function on your own, then you have to consider two factors. Okay, that the first one is actually the kernel function has the characteristic of a similarity measure. Okay, so yeah, kernel function is kind of similarity measure between two data. Okay, and the second thing you have to consider is not every function, not every random function can be a kernel function. Okay. If you pick a kernel function, then for that function to be a kernel function, it should satisfy what is called the Mercer's condition. Okay, we're going to talk about this next slide. Okay, so there are two things. And you want to come up with a new kernel function of your own, then that should be a similarity measure between two data. And secondly, that function should satisfy Mercer's condition. Then you can use that function as the kernel function. Okay. And if you go down here, this part is very important actually. So I said the only parameter you choose is the kernel function in SVM, and one of the advantage of using SVM is Yeah. Suppose you are the data you are handling is tree type, or it can be anything. It can be a graph type, or it can be image, or it can be sound, or it can be any arbitrary complex data type, right? So in that case, if you can come up with a kernel function for that particular data type you work on, then you are able to apply SVM to that data type. Okay. So, for example, if you the data you are handling is a graph structure, okay, so your data is not just a flat file. It is not database form, okay. It is more complex. It is represented as the graph structure, okay, whatever, okay, or very complex data structure, whatever it is, okay. Then actually, uh, you wanna apply SVM to that data type, okay? Then what you can do is first you come up with a kernel function for that data type, okay? Let's say it is network structure. Then you come up with a kernel function for that data structure, data type, okay? So I said the kernel function. When you come up with the kernel function, you have to consider two factors. Okay, the first one is kernel function is similarity measure. Okay, and the second thing is it satisfies Mercer's condition. Okay, so here your data type is graph structure, network structure, okay, and you want to apply SVM to the data structure, the graph data structure, right? Then what you can do is you come up with a similarity measure for the graph structure, network structure, okay, and you make sure that similarity measure satisfies Mercer's condition. Okay, then you are able to apply SVM algorithm to the data structure, network structure. Okay, that's the big advantage of using SVM. Okay, not many algorithms not many algorithms have these capabilities. Okay, for example, the deep learning, it is neural net. The basic assumption is the input data is flat, as you can see. This input data is flat. Okay, so if data structure is more complex form like network, tree, etc., basically you have to transform the input data into a flat form, okay, flat file or whatever. Okay, so so in that being said, this SVM is big advantage. Okay, you can as long as you can come up with similarity measure of the structure and that similarity measure satisfies Mercer's condition, then you have no problem of applying SVM to that particular data structure. Okay, that's big advantage of using SVM. When you run SVM, you have to choose a kernel function for SVM. So the easiest way is there are already a lot of the kernel functions, well-defined kernel function there. So you choose one of them and run it. Okay, that's very easy. Okay, and otherwise, if you wanna come up with your own kernel function, then in that case you have to consider two things. Okay, the first thing is the kernel function you are interested in should be similarity measure. So that means, so you have function, okay, and for two very similar data, the function value should be very high. That's the definition of similarity, right? And if you have two very different data, then the function value should be very small, right? By definition of similarity. So that's the first condition. And the second condition is that function should satisfy what is called the Mercer's theorem. It's written here. okay, that function should be semi-positive definite symmetric, okay. So if the function you're interested in is a similarity measure, has the characteristic of similarity measure, and it satisfies Mercer's theorem, then you can use it as a kernel function in SVM. Okay, that's the conditions you have to satisfy. Okay. So here you can represent the kernel function as a two-dimensional matrix, because in every kernel function it has two parameters, two parameters. Okay, so you can represent a kernel function as a two-dimensional matrix. Yeah, sometimes when you run SVM, most likely you define kernel as a function. Okay, but in some rare cases, some people you can define the kernel as a matrix, two-dimensional matrix. Okay, it's okay. It is okay. It is very rare though. Okay, so when you define the kernel as a two-dimensional matrix like this, you can do it. But in that case, this matrix should satisfy semi-positive definite symmetric here, semi-positive definite symmetric gram matrix. Okay, I don't go into detail of this. Okay, so if you represent kernel as a two-dimensional matrix, then this matrix should satisfy semi-positive definite symmetric gram matrix. Okay, then you can use it as a kernel function. This slide is just a reminder of what we have learned so far. Okay, and in a dual problem, we need to calculate the dot matrix, dot product of two mappings, right? But we are not able to calculate the mapping value of this. So instead of calculating each mapping value here, it's impossible, which is impossible. Actually, what we can do is we replace this whole thing by a kernel function. Okay, so by doing so, we don't have to worry about the number of dimensions and the configurations of the dimension, etc. Okay, everything is automatic. Okay, it's very nice and simple. Okay, that's the advantage of using kernel function. Okay, this slide is simply another example of using a kernel function. So when you choose a kernel like this, it is called a polynomial kernel. Then what happens is, actually, if you look at this part here, okay, it actually converts two-dimension into three-dimension like this. Okay, so it automatically increases dimension to three-dimension, and these are the configuration of the three-dimension. Okay, so that's what this polynomial kernel does when you use it. Okay, so as I said, we don't need to know all these things. We don't need to know the number of dimensions and configurations, etc. Okay, everything is done by this kernel function automatically. There are many kernel functions you can choose from in SVM. So these are some examples here. We have polynomial kernel, we have RBF kernel, we have sigmoid kernel. There are many more. I just put just a few examples here. Okay, so there are many there are many kernel functions you can choose from. So you can choose one of them and use it in SVM. Okay. So we have talked about the kernel function, and also the kernel function replaces the inner product of mapping here, right? So this is the original dual problem of SVM in feature space. That means this is the dual problem in expanded dimension, right? But we cannot solve it because we don't know what these values are. Okay, we don't know the value of mapping here. we don't know the values of mapping here, okay? So that's where we stuck, okay? But we have breakthrough. This part is replaced by a simple function called the kernel function, okay? You don't have to worry. So by using this kernel function, you don't have to worry about this, the mapping. You don't have to worry about this dimension, number of dimensions, the configurations, etc. Everything is automatic. This is very nice, clean, simple, right? So this is the final dual problem of SVM, okay, in the higher dimension, okay. So now by using this, we are able to solve this non-linear problem, okay. So this is the final dual problem of non-linear SVM, okay. So by solving the dual problem using kernel in a previous slide, now we are able to get the values of alpha. So by using alpha, now you can calculate the linear classifier of SVM, okay. So in original, the linear SVM, this is the line, equation of line, okay, linear classifier. So W is the slope of line, and this is offset. So W is like this. So do you remember when you determine the line, we use support vectors only, okay? So by using this support vectors, this is input of support vector, this is the label of support vector, this is the alpha of a support vector. By using this, we calculate slope W of the line here. By the way, this alpha value is kind of the importance of each data. Okay, you can regard this alpha value as the importance of each data. So, if a certain data is support vector, its alpha value is not 0. Okay, that means that data is important because it is support vector. For data which is not a support vector, okay, their alpha value is 0. That means that data is not important in terms of determining line, okay. So you can consider this alpha value as the importance of each data, okay. So anyway, by using these support vectors, you calculate slope W, and W comes here, and this is the final equation of line F, okay. So if you have new data Z, okay, and calculate F, if F value is greater than is positive, the class value is 1, and if F value is negative, this class value is 2 or whatever, okay. So that's how we classify new data. This is the final linear line. Okay, let's move on. Now we have a nonlinear case. So in nonlinear case, we use kernel function. Okay, so W, so you look at the original form. This is W, this is F. So these are transformed into like this. So X, original data X is now mapped toward higher dimension. So you have map pi x tj, okay, and this F here, this is represented as this, okay. Since we are using kernel, actually we don't know the value of this. As I said, we do not know the mapping value, so this one we don't have any idea, okay. We don't know this, so we cannot calculate W, okay. But even though we do not know the value of W, we are able to calculate the value of this by using kernel, okay. So we have this Again, we do not know the value of this, we do not know the value of this, but we can replace this by kernel function like this, okay? So this one here becomes this. So we use the kernel function. By using kernel function, we can calculate this. So we are done, okay? So f is this plus b. Again, we use the support vector only, okay? So the others are not important when you decide the line. Okay, that's how we calculate the classifier in linear case, in non-linear case. Okay. Now we have finished the basic theories of SVM. Okay. From now on, we're gonna cover a little bit of advanced stuff and some general comments of SVM, and that will be followed by some examples. Okay. So this slide is again the start slide, a little advanced stuff. So when we learn the neural net, we learned the gradient descent method, right? So the question is, can we solve this SVM using a gradient descent method? Right now, we solve the SVM method using optimized constraint optimization method, right? And in nonlinear case, and we add a kernel method as well. So that's the method for solving SVM, right? So we have another method, gradient descent, and we used it in neural net, and actually this gradient descent is used in many machine learning algorithms, right? So can you use gradient descent in SVM? Okay, so actually if we are able to, we can do it. Okay, so in linear SVM, we construct this Lagrangian function. Okay, and you take the derivative of j. Okay, so you get the slope, and using that derivative, you can use the gradient descent. You can do it. There's some restrictions here. Okay, you when you update your data, you just watch out these conditions. Okay, there's some so do you need a little bit of modification, but generally speaking, you are able to use gradient descent in SVM, in linear SVM. Okay. Okay, now for as for nonlinear SVM, so can you use gradient descent for nonlinear SVM? So let's take a look. So if the primal form of nonlinear or a dual form of nonlinear which contains mapping, then definitely we cannot solve SVM using gradient descent. Okay, this is not just the problem of gradient descent. Okay, this is just a problem in general because we have no idea of this mapping value. Okay, we cannot solve this problem. So we replace this mapping by kernel function right here, right? For this dual problem with the kernel, now we are able to solve this problem, okay, using gradient descent as well. You differentiate this, okay, also you have some constraint here, so we did some modification when you run gradient descent, but again, generally speaking, you are able to solve this dual with kernel, okay, by using a gradient descent, with a little bit of modification, okay. That is one assumption. We assume that this kernel function is differentiable, okay. That's quite a general assumption, okay. This should be differentiable, okay. This slide continues from previous slide. Okay, and then let's take a look at this formula. This is the final classifier form of nonlinear SVM, okay? And this is kernel function, and this is alpha. Alpha is the weight, the importance of each support vector. And we consider support vectors only in SVM, right? For the others, we don't care. These are the class value, label values of each support vector, okay? So when you're going to classify new data Z, okay, you calculate the use kernel function. Okay, so basically what you do here is for the new data Z, you calculate actually similarity between Z and for each of the support vector. Okay, so you're going to classify Z, new data, and you calculate similarity between Z and for each of the support vector here. Okay, then basically what you do here is you calculate the weighted average. This is importance of support vector. Okay, weighted average of this similarity. Okay, that's what you do in this SVM. Okay, so that way this whole thing is represented as a linear classifier. Okay, so this idea comes from the previous slide. Okay, that's another way of looking at SVM. Now we are almost done with SVM. The remaining parts are about the summary of SVM and some general comments of SVM, and it's followed by a couple of examples. Okay. So here, the Vapnik introduced Vishi dimension. Okay, and that represent the complexity of classifier or flexibility of classifier. So in SVM we minimize this, okay, and that means minimizing this actually minimizes Vishi dimension of classifier. Okay, so if you reduce Vishi dimension, actually it reduces the test error by the SRM method. Okay, I explained it in earlier part of this chapter. So minimizing this actually to maximize margin, we minimize this, right? So minimizing this actually reduces Vishi dimension of SVM. Okay, so when you reduce Vishi dimension, actually it reduces test error of algorithm. Okay, by the rule of SRM. Okay. So that's the basic idea how the SVM works. So SVM always looks for the best optimal line which separates two class values. Okay. Let me add one more. Okay. Perceptron is linear classifier, and perceptron also finds line. Okay, between two classes. That's linear. Perceptron is linear classifier. It also finds the line. Okay, then you may wonder what is the difference between the perceptron line and SVM line. Both algorithms look for line, linear line, for classification. Okay, so what is then the difference between these two algorithms? Okay, the difference is in SVM, the SVM looks for the best optimal line with maximum margin. Okay, it is guaranteed. Okay, so SVM line is the best optimal line with maximum margin. Okay, on the other hand, the perceptron line is not guaranteed. This line may end up any one particular line which divides these two class values. Okay, so there is no guarantee this line is optimal. Okay, you may end up in one arbitrary line, or you may end up in another different line. Okay, so there is no guarantee. So that's why this SVM is much better, okay, than any other linear classifier. Okay, it also solves the nonlinear problem as well. Okay, and another advantage is it's guaranteed to find the global optimal answer. Finally, this is another the advanced stuff here, and so we in primal form of SVM we minimize this. Okay, and that term is very similar to what is called rich regularization. We didn't learn regularization. We're going to learn this later in deep learning. So I'm going to give you a very short introduction here. Okay, so basically regularization is a way of a way of solving overfitting problem. Okay, so many learning algorithms suffers from overfitting problem. Okay, to avoid it, there are many techniques, but one of the most popular technique to avoid overfitting is using regularization. Okay, so in regularization, again we have many techniques there, but in regularization, one of the most popular method is to add this term in the objective function. Okay, so by adding this term in the objective function of learning, okay, we avoid the overfitting problem of algorithm. Okay, so you may not sure what I'm saying here. Okay, because we didn't learn regularization, but don't worry. Okay, just for now, this is advanced stuff, and we're gonna learn this regularization thing later in deep learning. Okay. When you run SVM, you have to choose the kernel function. Okay, so kernel function is pretty much the only parameter you use in SVM. So there are many kernel function in SVM you can choose from. Okay, you can choose one of them and run it. But which one is better? Unfortunately, we don't have a clear answer for that. Okay, so the rule of thumb is you choose kernel function, one kernel function, and run it, and you try this with different kernel function and compare the results. Maybe that's the rule of thumb so far. Okay, and for example, if you work on text classification, many people say linear kernel is the best option. Okay, but there's no guarantee. Okay, from the experience of running SVM, in text classification, linear kernel looks better, and in other application, this kernel may be better. Okay, but there's no guarantee. Okay, you can try and compare. Okay, these are strengths and weakness of SVM. Okay, until we had deep learning. Okay, actually the SVM was the most popular algorithm, and still it is a very, very popular and state-of-the-art algorithm. Okay, so let's take a look at the strengths and weakness of SVM. In SVM, training is relatively easy, and there is no local optimal. When you have answer from SVM, it is guaranteed that the answer is optimal answer. Okay, it scales well. Okay, even though we have a lot of data, it scales very well. Okay, in high dimension data. Okay, and you can process non-traditional data like strings, trees, or graph, or image, picture, whatever. I explained this in kernel function. Okay, that's a big advantage of SVM. And many other machine learning algorithms assume the input is given as a flat file. Okay, in the deep learning, as you remember, the input nodes are just the flat data. Okay, so if you want to process very complex data like string, tree data, or graph data, network data, or DNA data, or whatever, okay, then if you want to use those data in deep learning or other machine learning algorithm, you have to transform that data into a flat form. Okay, so that's the tricky part. Okay, but here in SVM, you don't have to worry about, as long so you just come up with a nice similarity function of that particular data type, then you are good to go. Okay, you come up with a kernel function for example, you are working on network data. Okay, then you want to use SVM, then you come up with a kernel function for the network data. Okay, then you are good to go. Okay, you just use that particular kernel function in SVM and just run it. Okay, then there is no problem. Okay, that's big advantage of SVM actually. Okay, and we can use the SVM for regression as well, okay, and that's another advantage. You can use this SPM as classification and also as a regression tool, okay. Weakness, you have to choose a kernel function, and there is no clear guideline of it. Maybe you just try different kernel and compare the result, okay. That's the only tool we have, okay. So this kind of weakness there. Okay, some other issues in SVM. SVM works only on in a real value space, so every data should be number. Okay, it doesn't process symbolic data. Okay, so everything should be number, real or integer. Okay, so that's the first issue, and SVM works on two classifications, binary classification only. Okay. So that's another issue here. So if your data is multi-class, non-binary, okay, then there are a couple of strategies to solve it, okay. For example, you can use one against rest or error correcting code, okay. You can use either of these, or there are some others too, okay. Basic idea of one against rest is, so let's say you have three class values, okay, then you have three SVM machine, three SVM algorithm, okay, and the first SVM, actually the role of first classifier is whether the output is class 1 or not, okay. For the second classifier, SVM classifier, the role is whether the class value is 2 or not, okay, etc. Okay, so that is one against rest. So combining all together, you can process multi-class problem, okay. And finally, the result hyperplane produced by SVM is not easy to understand because we are using kernel, okay. It produces some a nice looking hyperplane, but it doesn't explain how or why this plane is produced, okay. It is not easy to understand. It gives you very nice result, but it doesn't give you any explanation, okay. Why it doesn't explain why or how this hyperplane is produced, okay. It's the same in deep learning or neural net as well. It produces very nice result, but it doesn't give you any single hint about how these results are produced, okay. There is no explanation for that, okay. That's kind of a weakness of this method. This slide is the last slide I'm going to explain in this chapter, and this is about the SVM applications. Actually, SVM has been widely used in many different applications. And SVM was first proposed by these guys, Boser, Guyon, Bafnik, in 1992, and gained a lot of popularity in late 90, early 2000. Okay, so it shows best performances then. Okay, ranging from text to genomic data. Okay, as I said, SVM can be applied to many different data types, okay, not just flat data. You can use it for text, network, genomic data, whatever, okay. So I can apply this to complex data types. I told you graph, sequence, relational data, or whatever, okay. As long as you come up with a kernel function for the data type and it satisfies the Mercer's condition, then you have no problem, okay. You can plug that kernel function into the SVM and run it, okay, and it's very nice. You're good to go. So, and then SVM can also be used in regression problem, okay. You can use this to regression, you can use for classification, okay. So it's very popular. And SVM is kind of a black box, okay. It generates result, but it doesn't give you any explanation, okay. That is kind of a weakness of SVM.